Okay, we defined previously that I can represent any periodic function, so y of t does have to be periodic in nature, meaning it has parts that it repeats itself over time. So Fourier said that we can represent any periodic function by a constant term plus an infinite sum, so going from n equals 1 to infinity, of sines and cosines, and those sines and cosines have different amplitudes. So I'm going to write a sub n's for my cosine n omega naught t's, and omega naught, remember, is our fundamental frequency, plus b sub n sine of n omega naught t. And so any n greater than 1 will basically be giving me harmonics of that fundamental frequency. Right? But as we ended the last time saying, okay, this is wonderful and all, but if I actually want to take my square wave, for example, and represent that in this format as the sum of sines and cosines, I need to be able to figure out what I need to use for all of these coefficients, the a sub n's, a naught, and b sub n's. And we can start with a very simple system, or a very simple signal to just get the flavor of this. So y of t is going to be 2 plus 4 cosine of 2t. And automatically I can already tell some interesting things about this signal. So my fundamental frequency here, which is that omega naught, is going to be equal to 2 radians per second. Right? That's the lowest frequency content in the signal, the lowest non-zero frequency content in this signal. So I automatically define that as my fundamental frequency. And so then if I go in and look at, try to match up things here, I find that I only really have 2 coefficients in this particular signal. So I would have my a naught, right, is my constant term. So in this case that's going to be 2. And then my a1, I don't have any sinusoidal terms, any sine terms, so all of the b's are 0. So a1 will equal 4, right? And then all of the other a's are 0. So a2 through infinity are 0, and b1 through infinity are also 0. And so this would define, along with that fundamental frequency, omega naught is 2 radians per second, this would define a Fourier series. And so this is all the information that I would effectively need to reconstruct the signal at the end. And so you can start to see how I can get more compact representations of a particular data stream or signal with Fourier series. But obviously things don't come as neatly packaged as this typically. So if we want to just kind of come up with a more general approach to finding these coefficients versus just writing out all the terms and doing an exhaustive matching step with this, we'll start with a0. This is going to be the easiest one for us because that a0 is our constant term. Remember, there's no frequency. Effectively, I'm doing an a0 cosine of 0 times t, which is 1, right? So this goes to 1, and so I'm just looking at a0 here. And a0 we've already talked about to some degree. a0 is going to be our DC offset in my signal. So if I think about it, I have all of these sines and cosines, and sines and cosines, as we know, are going to vary between some -1 and +1. If I add some amplitude to that between negative an to plus an, negative bn to plus bn. So if I have some DC shift in my signal, that's going to be represented by this a naught term. Right? And so one very simple way to do it is kind of the basic approach we used previously in looking at a signal. It's just, you're just getting the mean of this signal. So in this case, it's very easy to see in this case that the mean is 1. Right, so this is going to be my a0 term, is going to be an amplitude of 1. But once again, that can be very hard to do on a real signal that you actually have coming into your Arduino or some other measurement system, for example. So let's go through a little calculus refresher very quickly. before we get to a more generalizable way of calculating not only A naught, but also ANs and BNs for any signal that you might have, any periodic signal that you might have. Okay, so quick refresher of your calculus. If I have an integral over a full period, so negative t over 2 to plus t over 2 of a sinusoid, and any harmonic, any of that fundamental frequency or harmonic of that fundamental frequency, if I take the integral of that, I'm going to get 0. Right? And the basic intuition behind this is if I have a sinusoid here, and I'm measuring the area, I'm integrating the area basically that's covered by these curves, obviously that's going to go to 0. And it doesn't matter how many cycles I have in here, as long as it is kind of still in that original period of the fundamental frequency. I'm still going to get 0 there. Right? And I can do the same thing for cosine. Right? A cosine looks something like this. Right? And so still I have this area here, this area here, and this area here, so everything cancels out and I still get 0 as long as I'm integrating over a period. It doesn't matter, once again, what n is. As long as n is not equal to 0, I'll say, right? If n is equal to 0, then I'm taking cosine of 0, which is 1. But in this case, sine n can be anything. And then we have more complex terms that we're going to have to deal with when we're trying to calculate these coefficients. So in this case, I have a multiplication of a sine and a cosine, and I can use some trigonometric identities in order to figure this one out. Okay, so in this case, when I have sine of some kind of integer multiple of my fundamental frequency times cosine of some other integer multiple of that frequency. In fact, m and n can also be equal in this case. Then I'm going to get 0, and that's because if I break this down based on this trig identity, I'm getting two sinusoids that are added together, right? And this coefficient is ultimately not going to factor into this, but I have a sine of m plus n times omega naught t plus a sine of m minus n omega naught t is equivalent to sine of m omega naught t times cosine n omega naught t, right? And I already showed that if I take the integral over this period of sine times some integer multiple of omega naught t, I'm going to get 0. So this term is going to give me 0, and this term is going to give me 0. So ultimately I have 0 of this integral as well. Okay, instead of having a sine times a cosine, if I have a sine times a sine, and potentially different or the same harmonics of omega naught here, also integrating over that same period, I can use, once again, another trigonometric identity to help me calculate this integral. Right, so in this case, here's the trig identity that matches up with these two sines. So I get an m minus n omega naught in one of these cosines and an m plus n omega naught as a frequency in another cosine. And I can see here that if m is not equal to n, or m is not equal to negative n, and I really only care about the positives for my Fourier series coefficients, if those are true, then these will be non-zero. And I already showed over here that if I'm taking integral of a cosine over that period of a non-zero n right here, I'm going to get 0. So this whole term here is going to be equal to 0 when m is not equal to n. Now when m is equal to n, I'm actually going to have this term collapse in m minus n will be 0. So I'm going to be taking the cosine of 0, which will be 1. This term will still be non-zero, so the integral of this will ultimately go to 0. So let's just look at this term to start. I'm going to end up with effectively a half that I'm integrating over. Alright, so if I do this integral, I find out that when m is equal to n, I'm going to get t over 2, half of my period, and then remember that's the fundamental period of my signal. So this is going to equal t over 2 when m equals n. And then if I take the product of cosines, once again integrated over that period, I'm going to be able to use a very similar trigonometric identity and get a very similar answer here. So I'm going to get 0 when m is not equal to n, and I'm going to get half of my period when m equals n. Alright, so to kind of go through the proof of how I would actually find a zero, I'm going to take the integral of both sides of this equation. So I'm going to take the integral over here, and I'm going to take that over a period once again from minus t over 2 to t over 2, because remember y of t is a periodic signal. And I'm going to take that, so dt here, I'm going to take that of all of these terms as well. Alright, and I dropped the minus t over 2 to the plus t over 2, so I hope you'll forgive me for that. But it was a little too onerous to write out. But in this case, I'm integrating over a period, right? And I'm integrating over a period of this cosine, right? And what we just showed in the last slide is that basically all of these are going to go to zeros, right? None of them have a zero coefficient there. All of these are also going to go to 0, and obviously this continues to infinity. All of those are going to be 0, so my only non-zero term is up here. And so I can rewrite that down here. So I'm going from the integral of minus t over 2 to t over 2 of my y of t dt is equal to the integral from minus t over 2 to t over 2 of a naught dt, and that's just a constant term there, so I'm going to get an a naught evaluated from minus t over 2, a naught t evaluated from minus t over 2 to plus t over 2, which gives me a naught t in the end. Right, so now I can calculate a naught from this equation. So a naught in the end is going to be 1 over t in the integral over a period minus t over 2 to plus t over 2 of y of t dt. And hopefully one of the things that you'll recognize here is that this was our same definition for calculating the DC offset of a signal, which is not surprising because this a naught term is representing the DC offset of our periodic signal. So I'm going to take a fairly similar approach to finding my other a coefficients, except instead of just integrating both sides of my equation, I'm going to multiply everything by a cosine n omega naught t first. Okay, and once I've done that, I'm going to take the integral of both sides of this equation. And once again, I've just written out some terms. You can write it in much more compact form with a summation, but I think this is a little more illustrative of how we're actually deriving the result for calculating these coefficients. So for each of these, I'm going to take the integral over a full period, so from minus t over 2 to t over 2 dt. And once again, if you'll forgive me, I'm going to drop the limits of my integral just to make my life a little bit easier. And so what you may remember from our little calculus refresher is that anytime I have the integral over a period of a sine times a cosine, that is going to go to 0. So all of these terms down here, regardless of m equaling n, those are going to go to 0. This a naught term, this is just integrating over a cosine. N is not equal to 0 in this case, so this will also equal 0. And then I need to go through these multiplication of cosine terms. And remember, these were also equal to 0 except for one case, and that was when these two frequencies were equal. So when I have an n omega t, or an n omega naught and an n omega naught here. So I can rewrite this whole thing down here, so minus t over 2 to plus t over 2. Right, so I end up with minus t over 2 to t over 2 integral of y of t cosine n omega naught t is equal to, I pulled an outside of here, so once again my limits are over that period, cosine squared n omega naught t dt, and if you remember correctly, this is going to give us an times t, our period, divided by 2. And so once again, if I rewrite this to try to calculate what an is, so in this case an is equal to 2 over t, and that integral, t over 2 of y of t cosine n omega naught t dt, and that will give me all of my n coefficients, my an coefficients, and so I can vary n here from 1 all the way up to infinity if I wanted, and find all of those a coefficients for any signal that I might have y of t. So I'm going to skip the derivations of the b sub n's because those happen the same way. Instead of multiplying by a cosine n omega naught t, I'm going to multiply by a sine n omega naught t, but I'll get effectively the same thing. And I can sum up my coefficients like this. So my a naught, or my dc term, is 1 over t, and I integrate over a period of my signal y of t dt. My an coefficients, I have a 2 over t coefficient here, minus t over 2 to t over 2 of that y of t, whatever my signal is, times cosine n omega naught t dt, and the b of n's are going to be very similar to that, except I'm going to be using a sine instead of a cosine. So minus t over 2 to t over 2, my signal y of t times a sinusoid at that particular harmonic, so sine n omega naught t dt. Right, and so all of these can give me the Fourier series coefficients of a signal y of t. And so once again, these coefficients are ultimately going into representing that random periodic signal y of t as this summation of sines and cosines.